Welcome to Brain Vision.
A typical scuba tank, when fully charged, contains 12 litres of air at 204 atmospheres of pressure. Assume an empty tank contains air at 34 atmospheres and is connected to an air compressor at sea level. And the air compressor intakes air from the atmosphere, compresses it to high pressure, and then inputs this high pressure air into the scuba tank. If the average flow rate of the air from the atmosphere into the intake port of the air compressor is 290 litres per minute, how long will it fully take to charge the scuba tank, assuming the tank remains at the same temperature as the surrounding air during the filling process? Right, okay, so we're going to start on a new page because it's a very long worded question. However, we need to break down the question into what it's actually asking us. So we're going to start from the ideal gas law. So but for two different scenarios. So P1 V1 equals N1 R gas constant T1. So pressure times volume equals number of moles times gas constant times temperature. Call that equation 1. And similarly, equation 2, we have P2 V2 equals N2 R T2, and we're going to call that equation 2, and we're going to do equation 1 divided by equation 2, which gives us P1 over P2, V1 over, that doesn't look neat, so P2 there, dot V1 over V2 is equal to N1 over N2 dot T1 over T2. And the information that we're given in the question is that the gas is at the same temperature, so we can immediately cancel these out because it's going to be the same, so the fraction is just 1. Similarly, because the gas is being filled, we're going from one system whereby we're filling the tank with no gas is lost in the process. So we're filling from the atmosphere at sea level into the compressor, into the scuba tank. So no gas is being lost in this system. So similarly, the number of moles that are being put into the tank are the same as the number of moles being taken out of the atmosphere. So N1 is equal to N2, so N1 over N2 is equal to 1, and similarly we can delete this fraction, or it is simplified to 1 in this context. We are being asked to find what the volume is that is being removed from the air, and then from that we can calculate the time because we are given a flow rate, so in terms of litres per minute. So our unknown quantity of air we will give by V2, so rearranging the equation to make V2 the subject, we have that V2 is equal to V1 P1 over P2. And V2 is unknown, but P2 is equal to, the pressure is equal to 1 atmosphere. So the pressure in the outside air is equal to 1 atm. And the pressure 1 is equal to, so if we think about this, our scuba tank is going from 34 atm to 204 atm. So if we think about what we're doing for the pressure, we're increasing the pressure is equal to, so we're increasing it by 204 minus 34 atm. So our pressure change is equal to 170 atm, atmospheres of pressure. So that's the pressure that we need to increase it by. And so also we have our volume 1, which is 12 litres. So the volume in the tank that we're changing through that pressure by, so V1 is equal to 12. So if we substitute in all those litres, and so if we substitute in all those numbers into equation, let's call this 3. So substituting these 3 numbers into equation 3, we get that V2 is equal to 2040 litres. And at the flow rate given of 290 liters per minute, so do V2, so to get the time, time is equal to 2040 divided by 290, which is our flow rate into the scuba tank from the outside air, and that gives us 7.03, which is equal to approximately 7 minutes as required.